So we have a box on a flat surface with someone pushing from one side and someone pulling from the other side of a rope. Pushing and pulling, they normally go in opposite directions, so if they're on opposite sides, they'll actually be going in the same direction. Friction opposes this motion, weight is counteracted by the reaction force, model this system. Okay, so the first thing you want to draw is a box on a flat surface. There's your flat surface, and there's our box. So we have someone pushing it, so if he's sort of standing this side and pushing it that way, the resultant force from him is going in that direction, so there's some thrust there. Just get rid of our little man there. And the other person who's pulling from the other side, so he's pulling from this side here, is going to be applying force in that same direction. So we can have two thrusts here, so we can call these T1 and T2. Then we have some friction. So friction opposes the motion. That means it's in the opposite direction. As always with friction, it's always in the opposite direction to motion. Okay, weight is counteracted by the reaction force. So weight goes straight down. The reaction force goes straight up, perpendicular to the surface. Okay, so those are all the forces acting on it. Just label those W for weight and R for normal reaction, and then this one F for friction. Okay. A good thing to remember is that the size of the arrow should indicate the size of the force. In this case, we're not told any magnitudes of forces. But a good thing to remember is, let's say if we had a particle here and you've got some force acting this way, and then you're told there's a force acting in the opposite direction and it's double the magnitude, well then, I know it's not perfect, but the arrow should be double the length. So the length of this arrow should be double the length of this arrow because it's double the magnitude. So a car is driving up a hill and is being towed by a truck from the top of the hill. Model this system on the car only. So we're not worried about what the truck's doing. We just want the force applied by the truck. Okay. So first it's going up a hill. So the plane's not flat. Well, it is flat, sorry. It's at an angle. So it's like that. Okay. So there's our plane. This is the hill. And we don't know what that angle is, but it's some angle. We'll call it alpha. Okay. Then we've got a car. I'm just going to model the car as sort of a box. I'm not the best artist, so I'm not going to draw a car. I'm just going to model it as a box. A box is absolutely fine. It serves its purpose and allows us to imagine what's going on. Let's think about the forces being applied. So it's being towed by the truck from the top of the hill. Okay? So it's going up the hill. So the truck is applying some force this way that I'm going to call T for thrust or tension or tow force, something like that. T's going up the plane. Okay? What else can we think of? Well, of course, the car has some sort of weight or mass, okay? So its weight always acts vertically downwards, straight to the centre of the Earth because of gravity, okay? So we have an arrow going down, okay? Well, there must be something stopping the car going through the plane then, because if there was nothing stopping it, and you might be thinking, oh, it's just the road. Well, the road has to apply some sort of force, and that's the normal reaction, which, as mentioned previously, always goes at 90 degrees to the plane. So that's 90 degrees there. Okay. Last, well, a car has tyres that roll on the road, which is going to have some sort of friction. Okay. So we'll have an arrow going down the plane because friction always goes in the opposite direction to the motion. Okay, if it's going up the plane, then friction must be going down. Okay, so a couple of things to note here. Notice how even though the normal reaction here that we can call R, and we'll call this one friction, we'll call this one W for weight. Notice, even though the normal reaction is meant to be opposing the weight pulling it through the plane, it's not acting completely opposite to it. Okay, and that's for two strict reasons. The normal reaction is always perpendicular, so this angle here is always 90 degrees regardless of what the model is. Weight always acts vertically downwards, so it has to be straight down even though we're on a plane. So think about it, if you use trigonometry, then part of this weight is actually pulling the car down the plane, and part of it is pulling it through the plane. Okay, so you could use trigonometry if we knew this angle and the size or magnitude of the force to figure out how much is pulling in which direction And of course, because the car isn't coming off the surface or going through it, then the normal reaction is completely equivalent to the component of the weight that is going this way, perpendicular to the plane.